Hi, I'm Tonio, and I'm going to show you how we are building goal-driven models of the sensorimotor system to understand human dexterity. But what are goal-driven models? In goal-driven modeling, we are beginning the modeling process by first identifying the regions that we want to have participate in the function that we are trying to investigate, as well as the pathways that lead through these regions, and we thereby inspire biologically our models. What we are not doing is to set the specific connectivity strength between the different neural populations within these regions, but instead we are training using deep reinforcement learning our complex recurrent convolutional neural network on a human task under humanoid constraints, under the premise that if these constraints are strong enough, that then the emerging neural computations will resemble those that we find in the brain. And such constraints can, for instance, be the use of anthropomorphic robots, like the ones for a hand shown in the slide here, and the use of only humanoid sensation as an input to our model. Now, if that's true, if the neural computations we find in the model resemble those of the brain, then we can better analyze these neural computations than the actual brain, specifically with regard to more complex things like transformations between representations. And based on this, build new hypotheses about, for instance, sensorimotor processing, and compare that to human data in the end. But first, let's have a closer look at the first point that I made regarding how we are inspiring the model, how we are aiming for macro-scale plausibility in our models. The first step we take here is to look at the functional neuroimaging literature in order to identify the regions that take part in sensorimotor processing, and in our case, specifically in dexterity. Then we are turning towards the eBrain's multi-level human brain atlas in order to extract data about the structural connectivity between these regions in order to build these pathways that I've talked about before. Using this approach, we've built this model here of the frontoparietal network, and as you can see, it covers the entire perception action loop. We are starting with sensory cortices like the visual cortex and the somatosensory cortex that build abstract representations of proprioceptive and touch information as well as visual information, which are then integrated by the posterior parietal cortex and compared to a goal description by the prefrontal cortex, to then ultimately, through the motor cortex, lead to a motor command that is executed at every time step in our simulation. In order to get the connectivity into this model, because as I said before, so far what we have is only the broader architecture, the macro level architecture, where we have regions and how they are connected, but not exactly the weights between them. To change this, we are training this on an ecologically valid task, in-hand object manipulation, a task that is relevant to a human on an everyday basis. And we prototype this task by formulating it through the objective of rotating a block in the hand, as shown here on the slide, into a target orientation. And since we are using reinforcement learning to do this, we need a reward in order to formulate this objective to the model. And we do this by simply rewarding the progress that the hand makes towards the target orientation, as well as a punishment for dropping the block, and a strong reward for a successful reorientation. And then the hand can do up to 50 reorientations within one episode, but needs to stay within a timer of 8 seconds. And every time it can successfully reorientate a block, the timer gets reset. The inputs we feed to our model are readings from a camera, readings from 92 touch sensors on the palm and the fingers, and the joint angles and velocities. And that means that we are solely using raw sensory information that a human agent would also have access to. Now, training this model results in the learning graph that you see on this slide here. And On the x-axis here you have training time, and on the y-axis accumulated reward over an average episode. And as you can see, our own model in blue here, despite using only humanoid sensation and a plausible network architecture, is able to be very competitive with the state-of-the-art in AI, which is depicted in orange here. On the right to it, you can also see the hand performing, or the model rather, performing the task by steering the anthropomorphic robotic hand. And as you can see, it's quite capable of reorientating the block. In fact, it can chain up to about 40 such reorientations without failure. And it also adopted some human-like strategies, like for instance, the usage of the opposable thumb in order to rotate the block around one of the axes. Because this training such a complex model, it's a recurrent convolutional neural network, it's super large scale in its parameter count, and also in the complexity of recurrence, etc. This is quite the difficult engineering task to train this on such a complex application like in-hand object manipulation. And because we want, of course, to also encourage others to take this approach but not have them repeat our efforts, we are also making available our software in a high-level API that is usable without understanding much about reinforcement learning, let alone the efforts of distributing computation on HPC clusters. And we're making this available through AngoraPy, which you can just use through GitHub, the Python packaging index, and also as a Docker environment. And we are at the same time also working together with the people from the technical coordination team of eBrains to make this available as an eBrains workflow. Now, the next step from here, after we've now arrived at a model that has both the architecture but also the connectivity that gives rise to functional validity, the next step is to do an analysis. And this analysis can, for instance, be, as shown here in the slide, as some sort of in silico decoding study, where we are investigating how well we can predict different pieces of information from the representations we find in the different regions of the model. By looking at the representations, we can also conduct things like representational similarity analysis in order to validate our model against human data from neuroimaging. And given sufficient validation, we can then generate new hypotheses, for instance, by analyzing the dynamics in the network or the transformations between representations. And given these new hypotheses, we can then design new experiments in order to test them and thereby ultimately, hopefully, understand more about how the human brain controls hand movements. That's it. If you have any questions, feel free to ask.